What lies beyond the farthest edge of the universe? Not just beyond the stars or the galaxies or even the cosmic microwave background, but past the very limits of time, space, and understanding itself. Scientists have mapped the observable universe to astonishing precision, yet beyond the cosmic horizon is a realm untouched by light, unreachable by telescopes, and unexplained by our best theories. Is there more universe out there, or something entirely different? In this deep dive documentary, we'll journey to the limits of known science and step into the unknown, exploring every wild possibility: parallel realities, multiverse bubbles, cosmic mirrors, and the haunting silence of true nothingness. The observable versus the entire universe. The universe that we can see is about 93 billion light-years across. That's because the universe has been growing since the Big Bang. The space between galaxies has grown a lot in the 13.8 billion years that the universe has been around. Light from the farthest reaches has just barely made it to us, leaving us with a limit that we can't see past. We can't change this because of our technology or our lack of knowledge. It's just how reality works. Since the beginning of time, no matter how good your camera is, you can't see past the speed of light. And here's the twist: beyond that edge, the universe may go on forever. Picture yourself floating at night in a huge ocean. In the distance, you can see a ring of sparkling city lights. This is the only sign of society you can see. You don't know how far the towns go out into the distance, or if that's even where the world stops. That ring of light is like the universe we can see. It's just a small part of it because light has to travel a long way to get to us. There could be more stars, galaxies, science, and maybe even things we've never even thought of beyond it. So how do we define the entire universe? That's a question that borders on the philosophical as much as the scientific. The observable universe is what we can study, but the full universe is what is, and the gap between the two might be staggeringly large. A lot of people agree with inflationary theory, which adds to the Big Bang model and says that the universe grew very quickly in the first few fractions of a second after it was created. It was during this increase that quantum fluctuations were spread out over very large areas, setting the stage for the large-scale structure we see today. But inflation doesn't always stop all at once, and in many models, it never does. Eternal inflation is the name for this, and it makes people think that the universe may only be one pocket in an endless number of them. If inflation did continue beyond our cosmic horizon, then there could be a near infinite expanse of universe out there, identical to ours in some places, bizarrely different in others. Galaxies might form under the same laws of gravity and thermodynamics, or maybe other regions have different values for the fundamental constants of nature, making life, matter, or even atoms impossible. And we would never know, because no information can reach us from those places. The fact that we can't connect with most of the universe is built into the very nature of physics. The speed of light is not just a guess, it is the fastest thing that can ever be. There is no way to go faster. In other words, the world may be endless, but our understanding will always be limited to what we can see. Some cosmologists use the form and curve of space to try to guess how big the whole universe is. So far, all measures point to space being flat. If that's the case, it could go on forever. But it's possible that the universe has a limit, even if space is flat. It could wrap around itself in strange and interesting ways. In theory, you could go in a straight line for billions of years and never come across an edge. You would always end up back where you started. That said, when we observe the cosmic microwave background, the oldest light in the universe, frozen just 380,000 years after the Big Bang, we see patterns that seem to suggest uniformity beyond the observable edge. There's no obvious boundary, no sign of a wall, no abrupt end to the stars, just more of the same, as far as the eye and light can see. But there's more than just a technical difference between observable and entire. It changes everything about our place in the universe. If the world is endless, then the area we can see is just a small part of an infinite unknown picture. It's possible that one day we'll be able to plan out the whole thing, or we might see strange signs coming from across the curve of space. No matter what, though, the sky we see now is not the end. It's the most light has given us so far. And even that is slowly changing. Every second, light from further and further away is reaching us. The observable universe is growing, but ironically, the galaxies beyond our reach are also accelerating away due to dark energy. Some galaxies we can see now will eventually become unreachable forever, their light stretched into invisibility. The edge, in a sense, is both advancing and receding, a cosmic tide we can never quite catch. When someone says the edge of the universe, know that it's not a wall, a cliff, or the end. It's a line that's drawn in time, not place. A limit set by light, speed, and the fact that space is always getting bigger. And beyond that, maybe more galaxies, maybe another universe, maybe the end of physics as we know it. The horizon of time. When we talk about the edge of the world, we usually think of a faraway border or a line that there is something beyond. Need more room? A wall? Nothing? Cosmology today, on the other hand, turns this thought on its head. Space is not where the real edge of our universe ends. It's on time. To understand this, picture the universe as a bubble that is getting bigger. You're a tiny dot on the top of the balloon, and as it gets bigger, other dots get farther away from you. Now for the important part. That balloon's surface doesn't have any edges. Only where you can see ends up being the edge of its surface. And that edge is not based on distance but on time. This limit is called the cosmic horizon, and it's set by the age of the universe. Light takes time to travel. So when we look deep into the universe, we are looking into the past. The furthest light we can see comes from about 13.8 billion years ago, the moment of the Big Bang. But because space has expanded since then, that light now comes from regions roughly 46 billion light-years away. This mismatch between time and distance is a key feature of cosmological expansion. So when we ask what exists outside the observable universe, what we're really asking is, what exists beyond the reach of light that has had enough time to reach us since the Big Bang? The edge is therefore not a spatial edge, it's a temporal one. Imagine lighting a candle in a vast dark cave. At first, the light reveals only the area nearby. As time passes, the glow spreads, illuminating more and more. The edges of the light are not the edge of the cave, they are the limit of how far the light has traveled in time. Likewise, our instruments can only detect as far as photons have had time to journey through the universe's expanding fabric. This idea is called the particle horizon, and it shows how far particles could have moved to reach a viewer in the early universe. But there's another one that might be even stranger, the event horizon. The particle horizon tells us how far we can see. The event horizon, on the other hand, tells us how far we can ever see, even in the infinite future. These things happen because dark energy is speeding up the spread of the universe. We can see some galaxies today, but they're moving away from us faster than the speed of light, because space is expanding. It's not that the galaxies are moving quickly through space, but that space is expanding. Their light will never reach us again one day. They will be out of our reach forever. This means there is a cosmic cutoff, not just in what we can observe, but in what we ever will be able to observe. The universe, in a real and measurable sense, is retreating from us. But this horizon of time does more than just limit our vision. It defines the boundary of our knowledge, our models, and even our capacity for meaning. Beyond this temporal veil, there may be entire civilizations, galaxies, or even physics that we will never know about. Not because we're too primitive, but because the structure of reality itself prohibits it. And yet, the horizon of time is not fixed. It's dynamic. With each passing second, more photons arrive, a deeper look into the past. New discoveries are made possible with each moment. When the James Webb Space Telescope peered further than any previous instrument, it was stretching our temporal horizon, catching light from just a few 100 million years after the Big Bang. In doing so, it deepened our understanding, not just of the universe's scale, but of our place in time within it. There is also a metaphysical component to this. The time horizon is like a psychological boundary, and not just in a cosmic sense. It's also a boundary in how we think about life itself. The idea that some parts of the world will always be out of reach, unseen and unknown, makes us wonder what it means to live. If there are galaxies whose light will never reach us, do those galaxies really exist in our universe? Or are they two different realities? Then there's the problem of simultaneity, or how to define now when people are very far away from each other. Time and space are not absolute in relativity. There are times when two events happen at the same time that are not the same in other frames of reference. When you look at it on a cosmic level, this is more than just a thought experiment. It limits how we can describe the present moment in a world where motion and gravity make clocks tick at different speeds. When we look at a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago. But what is it doing now? That question is meaningless in relativistic terms unless we define a frame. And in cosmology, that's not easy. Our now is local. Every region of space carries its own version of the present. So even if we could break through the horizon of time, we'd be reaching into something else's past, or future, not our shared now. Time, in this sense, is the ultimate boundary, not space. This realization changes how we conceptualize the universe's edge. There is no wall, no fence, no limit we could travel toward and eventually reach. Instead, there is a vast and ever-growing silence, a boundary defined not by distance but by delay, and that delay is infinite for some things. Their light will simply never arrive. But this is also beautiful, because time is what lets us see the universe. Everything would fall into a single moment if there were no weight, limit, or distance. It would be flat and lifeless. The universe instead unfolds slowly, like a story told through light, with each photon bringing a thread of the story through the ages. Is the universe finite or infinite? Is the world limited or infinite? This is one of the most difficult questions that people can't answer. To answer that, we must first separate the ideas of what we can see from what might really exist. It's a sphere about 93 billion light-years across. This is the part of the universe we can see. In no way does that mean the universe is 93 billion years old. For that reason, even though the universe is only about 13.8 billion years old, space has been growing the whole time. The light from the farthest galaxies has been moving for 13.8 billion years because of this. But those galaxies are now about 46 billion light-years away from us because of the expansion. That's the size of our observable bubble. But what lies beyond? There are three main possibilities, each more mind-bending than the last. 1. The universe is finite but unbounded. It's hard to understand this idea. Consider the Earth's surface. You will never fall off an edge if you walk in any way. It's true that the Earth has a limited surface area, but it's also true that the Earth has no edges or borders. If you have enough goods, you could walk on forever and never hit a wall. Now take that two-dimensional analogy and expand it into 3 dimensions. In this model, the universe might be like a 3D version of the surface of a sphere. It's finite, yet it curves back on itself. If you could travel in a straight line long enough, faster than the universe is expanding, you might eventually return to your starting point, just as a person walking around Earth ends up back where they began. This type of universe would have positive curvature, similar to the geometry of a sphere. But here's the catch. There's no visual curve in the way your eyes might detect, because space itself curves and you're moving through it. Every step you take feels straight. It's the universe that's looping, not your path. 2. The universe is truly infinite. Many cosmologists agree with this point of view. Space goes on and on in this form. There is no limit, edge, or road that goes back. There is nothing but an endless universe. stretching out in all directions and full of galaxies, dark matter, radiation, and maybe even some physics rules we can't even think of. If the universe is endless, it means a lot of amazing things. One reason is that there might be another form of you out there. There could be an infinite number of you. Why? Since there is only so much matter in the world and only so many ways to arrange it, every possible arrangement must finally happen again, just like rolling a dice enough times. The cosmic doppelganger hypothesis is the name of this idea. That's not science fiction. It's a possible result of an infinite number of events. Our visible universe is a drop in an endless ocean of galaxies. It's a small patch of sky in a field of galaxies that has no end and no way to know it. How do we test for infinity, though? The truth is that we can't. Not right away. We're not able to send probes past the horizon. We can only see what we can see in the visible world. That's why we use math. 3. The universe is flat, and that might mean infinite. We can figure out how big the universe is by looking at its shape. Using geometry, we know that the universe is almost flat. This is because of research into the cosmic microwave background, CMB, especially work from the WMAP and Planck probes. Flat geometry is what you'd expect in an infinite space. If you draw a triangle on a piece of paper, the angles add up to 180 degrees. That's flat geometry. Do the same on a sphere, and the angles add up to more than 180 degrees. That's positive curvature. Do it on a saddle-shaped surface, and they add up to less. That's negative curvature. The fact that our universe appears flat suggests either that it is infinite, or that it is so large that any curvature is beyond our ability to detect, like standing on a beach and trying to prove Earth is round with your own eyes. This has something to do with the idea of cosmic inflation as well. The universe grew very quickly in the first fraction of a second after the Big Bang. In the same way that blowing up a balloon makes a small patch look flatter, this got rid of any curves. The observable universe would look flat if inflation lasted long enough, which we think it did. This is true even though the world is curved on much bigger scales. Finite yet edge-free. This is where things get really weird. There is no such thing as an outside even if the world is limited. You can't point to a wall or an edge. A finite world doesn't need a cosmic fence, just like the top of a balloon doesn't need an edge. As if a hypersphere were to curve through higher dimensions, space could be closing in on itself. You'd never reach the end because there is none. The journey would just keep cycling you back through space-time. This brings us to an important philosophical shift. The universe isn't expanding into anything. It's expanding within itself. Space is being added between objects, not at the outer rim. In fact, asking what's outside the universe may be a meaningless question, like asking what's north of the North Pole. In general relativity, space and time are the fabric of the universe. Without them, there is no framework in which outside can even exist. Implications of a finite versus infinite universe. Whether the universe is finite or infinite changes how we think about everything, from the ultimate fate of the cosmos to how we define meaning, to whether we are truly alone. If there are limits to the universe, then we might be a part of a closed loop or a cosmic island with limits that are written in the laws of physics. There might only be one Earth and one you, for example. If it's endless, though, the story gets weirder. There may be more than one account of events out there. Every possible result, every wish or fear comes true in a faraway part of the multiverse. Space expands, but into what? If there's one question that consistently breaks brains, even among physicists, it's this. If the universe is expanding, what is it expanding into? At first glance, it seems like a pretty simple question. A balloon grows into the air around it when we blow it up. A drop of ink that moves through water flows into more water. Everything we go through turns into something else. It makes sense to think that the universe is expanding into a bigger empty space, like a huge outside room stretched out in a cosmic temple. But the truth is weirder, very strange. The universe is not growing into anything, according to general relativity and the best models we have of the universe. It's not pushing into a place that's already there. Instead, space is getting longer. Things are getting farther apart, not because things are moving out into a bigger box, but because the box is getting bigger. Let us break that down into its parts. In cosmology, to understand what expansion means, we need to look at the idea of the metric, which is the mathematical structure that describes how far things are apart in space-time. In an expanding universe, the metric isn't constant. The scale factor, a part of the metric, increases with time. What does that mean practically? It means that over time, the ruler we use to measure space is growing. Two galaxies that were once 1 billion light-years apart may now be 2 billion light-years apart, not because they've moved through space, but because the space between them has grown. This idea is embedded in the Friedmann-Lemaitre-Robertson-Walker metric, a solution to Einstein's field equations that models a homogeneous, isotropic expanding or contracting universe. It describes how distances between objects change over time due to the dynamic geometry of space itself. Space isn't growing into a box from this point of view, it's just getting bigger. It's not sharp, not a limit. So there is no outside. A popular way to explain this is with the example of a balloon rising. It's like putting little dots on the top of a rocket. The dots move away from each other as the balloon gets bigger. They're not moving on top of the surface is stretching. Now, picture the surface as a universe with only 2 dimensions. It gets farther away as it grows, but there is no center on the top. Each point can see how the other points are going away. But this comparison also makes things more confusing. We use a room to blow up a balloon. The balloon is rising into the air around it, which is a 3rd dimension above the surface. Because of this, when we think of the world growing, our brains naturally want to picture a 4th dimension into which it grows. But here's the catch. Our models don't have any outside dimensions. There is no outside in the world. It's a lively shape that stands on its own. There is no outside cause for the growth. Space is getting bigger. The idea that the world is spreading outward from a central point is another false idea. That's not how the growth of space works. In the universe, each point can see every other point going away. There isn't a middle. There is no best place to be. From a galaxy 10 billion light-years away, you'd see the same thing we do. Galaxies coming together quickly in every direction. The universe seems to grow around each person who looks at it. In a universe that is homogeneous and isotropic, the same in all directions, there is no center at all. This doesn't mean that each of us is the center of the universe. It's not linear, but geometric. That expansion is. What's past the edge then? There is nothing there, not even space as we know it. It's not that there's nothing out there in the world that needs to be filled. There is no place outside of the world. The idea of beyond doesn't work here. At least from what we know about science right now, there is no space, time, or structure outside of the expanding world. According to brain cosmology, some theoretical models say the universe could be embedded in higher dimensions, with a brain floating in a collection of higher dimensions. So it's possible that the world is growing into a place with more dimensions. But that's not the same idea that standard general relativity talks about. For growth to happen, you don't need to assume an anchoring space. Expansion can only be explained by how the world works on the inside. You can figure out how far apart galaxies are, how fast they are moving away, and how redshifted their light is without ever mentioning an outside. Another way to look at it. When we use the word expansion, we mean that something is changing into something else. In the case of the universe, however, growth means that more room is being made. A longer way, more space. Not interested in something else, I just want more. We're not completely new to this. Every second seems to appear, but we don't question what time is growing into. Time just goes by. Bigger than that, the same is true for space. When you look back in time, this makes sense too. It gets smaller, denser, and hotter as we move farther back in time to the Big Bang. If you keep going, the scale factor will finally get to zero, which is called a singularity. We don't think it shrunk from something smaller though. It was what it was, small and contained. Going forward, it's the same. It just gets bigger. It's not growing into anything at this point. There is just more room being made. People have been wondering for thousands of years, what lies beyond the stars, at the edge of the sky, and at the end of the universe? That line has been pushed farther with each new science change, but as the universe grows, we see something we've never seen before. There is no edge at all, and this might be scary. We want edges to keep us safe. We need a box to store things in. Our brains have evolved to think about things as being in rooms, seas as being on planets, and galaxies as being in worlds. The world is not a thing though. It's a field, which is a shape-shifting, law-governed framework of space-time. This question, what lies outside the universe, might be like the question, what lies outside mathematics? It's a meaningless question with no answer. Still we ask, because people like to explore, not just of seas, stars and atoms, but also of thoughts that are too big to put into words. What the universe is growing into is not just a question of cosmology, it's also a question of the boundaries of what we can think. The universe has no center. When you're floating in space, there are so many galaxies around you that it can get dark. You might wonder where the center of everything is. Where did the Big Bang take place? From where does everything grow? The truth, though, is that the world does not have a center. It didn't go off in space like a bomb from one spot. It wasn't a blast from the outside into space. The Big Bang did not happen in a certain place. It took place everywhere because that's when space was born. Assume a sheet of rubber that goes on forever and stretches in every direction. There are points on that sheet that move away from each other as it gets longer. Everything on the sheet looks like it's getting bigger around you, no matter where you stand. But there isn't a special place. There's no center. Just add more rubber. That's the way our world works. We can see galaxies moving away from each other in all directions when we look out into space. They're going away faster, the farther away they are. This is Hubble's law, and it's true everywhere. You would see the same thing from a galaxy 10 billion light-years away, galaxies moving away from you in every direction. It would make you feel like you were in the middle. But that illusion is everywhere, because the universe isn't expanding from a place, it's expanding between places. This is one of the most profound and difficult ideas in cosmology, because it defies everything our intuition tells us. We're used to objects having centers, our planet does, our galaxy does, even a hurricane spirals around a central eye. But the universe? It has no edge, no outside, and no middle. The universe is homogeneous, the same everywhere on large scales, and isotropic, the same in every direction. These two principles, known as the cosmological principle, are fundamental to our best models of the cosmos. And yet, it feels wrong. How can everything be expanding if there's no origin point? How can there be motion without a center? So let's use the balloon again. But be careful. If you blow up a balloon and draw little dots on it, the dots will move away from each other. They are not all in the middle. While the center of the growth is inside the balloon, the top of the balloon is like our three-dimensional space, which is made up of 2 dimensions. That means the center isn't on the outside. It doesn't exist in the world of the comparison. In the same way, the heart of our world is not in space at all. It's not anywhere. Or maybe I should say that it's everywhere. When we say everywhere, the Big Bang did not mean that there was an explosion that sent mass into space. In other words, space was smaller, hotter and denser, and then it grew bigger. It grew, and so did the locations we used to talk about it. There was no place to grow outside. There is no set point to move away from. In this way, the universe is like a fabric without seams or threads pointing to a middle. And if that's not strange enough, consider this. Even if the universe is finite, like the surface of a sphere, it can still have no center. Think about being on Earth. You can walk in a straight line forever without falling off or hitting a wall. Earth is a finite sphere, but it has no edge. And no point on the surface is the center of that surface. It's just curved in a way that loops back on itself. If our 3D world has a similar shape, like a sphere with 3 spheres inside it, then it might be limited in size, but not limited in scope. There are no walls, there are no edges, there is no middle. That's why the answer to "where did the Big Bang happen?" is right here. Also everywhere else. All of space and time were once packed into that unbelievably hot and thick state. It's not just an idea either. What has been seen supports it. We can see that the cosmic microwave background radiation is coming at us from all directions. You wouldn't think that if there was a center somewhere. All over the place, that sounds like the echo of a beginning. We're not off to the side. We are not in a neighborhood of space, far from the action. We're also not the most important thing in the world, or at the center of everything. We are only a small part of a huge, growing whole. Nowhere is the heart, and everything is somewhere else. And that truth might be the most humble of all. The holographic principle. Visualize yourself holding a snow globe. Inside is a small world, maybe a winter town or a castle surrounded by snowy wonder. Imagine being told that everything that's going on inside that globe is written on the glass's surface in some way. Not just a picture, but the whole scene's physics, down to the last speck of snow, wind gust, and second of time written in 2 dimensions on the outside. That's the basic and mind-bending idea behind the holographic principle. It suggests that all the information about our 3-dimensional universe, including everything happening inside it, may actually be described by information encoded on a distant 2-dimensional boundary, a kind of cosmic screen. Like a hologram, the 3D world we experience might be a projection of a deeper, lower-dimensional reality. To understand why physicists even entertain such a wild idea, we need to begin with black holes. In the 1970s, physicists like Jacob Bekenstein and Stephen Hawking began exploring the thermodynamics of black holes. They discovered something astonishing. The amount of information, or entropy, that can be stored in a black hole is proportional to the surface area of its event horizon, not its volume. This was strange. In most physical systems, entropy, a measure of disorder, or the number of microscopic configurations, scales with volume. A room filled with gas molecules, for example, has entropy that depends on the space the gas occupies. But black holes don't work like that. The amount of stuff a black hole can hold seems to depend on its skin rather than its insides. One bit of data spread out over a Planck area, which is the tiniest possible area of space, equal to about 1035 meters squared. This made me think of a strange but strong idea. Maybe black holes are just the start. This could be how the whole world works. This brings us to the holographic principle, first proposed in the 1990s by Gerard 't Hooft and later expanded by Leonard Susskind. It proposes that all the information contained in a volume of space, even our entire observable universe, might be encoded on its boundary surface. It's a radical departure from how we normally think about reality. But in 1997, it gained serious traction through a breakthrough called the ADES-CFT correspondence, a mathematical duality discovered by theoretical physicist Juan Maldacena. In short, there is a mathematically identical description that lives completely on the border of a certain type of spacetime called anti-de Sitter space, ADS. It is called a conformal field theory, CFT. Equations on the outside can explain everything that is going on inside the room. These 2 hologram states are very useful in string theory and quantum gravity. One world with gravity and one world without gravity can be 2 sides of the same coin, even though they look very different. Our universe is not ad space. Instead, it is flat or slightly positively curved space-time. However, the similarities point to a deeper idea. Perhaps our universe is also an image. If it's true, It would change everything about how we see ourselves. Think about this. What if the very edge of the universe holds information about every planet, star, particle, and moment in time? It could even be on the cosmic horizon, which is the farthest distance light has had time to reach us since the Big Bang. That edge, which is 46 billion light-years away in all directions, could serve as a screen, a flat surface that stores the quantum information of everything inside it. And we, living our three-dimensional lives, are simply experiencing the projection of this information as physical reality. But how can this be? How can we be shadows of something more fundamental? We'll look at holograms again to help you understand. You can find these on credit cards and unusual things. When lit properly, a flat surface with tiny interference patterns can make it look like it has depth in 3 dimensions. There is a lot of information on the surface, but the experience feels like it has depth. When you look at the holographic principle, this comparison is taken to its logical conclusion. It's not just an illusion of depth. Everything in reality, from quarks to awareness, comes from a deeper 2D layer that we can't see. Of course, this is still just a lot of theory. We still don't know if the world really works like a hologram. But there are some enticing hints. For instance, the entropy bounds derived from holographic arguments match those found in cosmological models. Attempts to unify quantum mechanics with general relativity, especially in quantum gravity research, find common ground in holographic approaches. And in some models of the early universe, the inflationary period might have imprinted holographic information on the cosmic microwave background, subtle signals that astronomers could one day detect. It also has very important philosophical consequences. What does it mean to be in a certain place if the world is a hologram? Does space itself appear, meaning it's not a real thing, but a useful illusion? Is gravity really just the sound of more complex quantum reactions happening on a flat surface somewhere outside of our perception of reality? Also, this is very strange. If reality is stored on a surface, what's below that surface? What does the holographic principle have to do with our search for the edge of the universe? There might not be a wall in space if there is a limit. There might be a limit in knowledge, a spot where the information about our world is kept, like the edge of a hard drive where the program is kept. This edge might not be in space at all, though. It could be math, in code, in the reasoning of pure quantum. So, the holographic principle doesn't just point to what's outside of space and time, it changes the whole question. The edge might be the code itself. What happens when that code runs is what we see, hear, feel, understand, and even think. Still, we don't know. But by thinking about it, we are already pushing the edges of what is real. Brain cosmology. What if the world we live in is only a small part of a much bigger, more complex one? This is the main idea behind brain cosmology, a theory based on string theory that says the universe is made up of a three-dimensional fabric, or brain, that is surrounded by a higher dimensional area. The word brain comes from the word membrane, but you wouldn't find it in a biology book. It's a theory that could completely change the way we think about life. In our everyday experience, we live in 3 spatial dimensions: up, down, left, right, forward, backward, and one of time. But string theory, the mathematical framework that attempts to unify all the forces of nature, proposes that more dimensions might exist. In some versions, there are 10 or even 11 dimensions. Most of them are compactified, curled up tightly on scales too small to detect. But a few might be extended in ways that allow entire universes, like ours, to exist as 3D brains floating inside a higher dimensional space called the bulk. In this scenario, we're confined to our brain. Everything we know, atoms, light, gravity, mostly planets, and even ourselves, is stuck on this 3D surface. The particles and forces of the standard model of physics are localized to the brain, meaning they can't move into the higher dimensions. But the bulk, the multi-dimensional space in which brains reside, could contain other brains, other universes, and maybe even entirely different laws of physics. Amazing things happen as a result. One of the most interesting things about brane theory is that it suggests there might be other branes moving around in the mass with higher dimensions. These branes might be other worlds, each with its own galaxies, matter, time, and maybe even different kinds of life that are controlled by different laws of physics. Gravity is one of the few forces that can leak into the mass, so even though we can't directly affect these branes, we might still feel their pull. This idea helps to solve a puzzle that has been around for a long time. Why is gravity so much weaker than the other basic forces? If gravity can spread into extra dimensions but not other forces, then the gravity we feel on our brane is weaker than it is elsewhere. This leakiness might be a sign that experiences on higher levels are not only possible, but required. One theory, called the ekpyrotic universe, says that the Big Bang wasn't the start of space and time, but rather the result of two branes colliding with each other. They released a huge amount of energy when they hit each other in the bulk of higher dimensions. It was enough to start the fast growth of our universe. From one point of view, this brane crash would have caused what we now call the Big Bang. From another, it was a cosmic rebound, a part of an endless series of collisions and growth. Imagine two huge, unseen sheets moving through an ocean of other dimensions. When they hit, boom, there is a birth. Then they move back together, and the process starts all over again. From this point of view, the universe is not a single event, but a process that goes around and around and has no real beginning or end. What else is there besides our world in this model? There could be a whole family of universes or other branes with their own laws and developing in their own way. Some might be completely alien, full of strange matter and shapes that you can't even imagine. Some others may look exactly like ours. There are also some that may be only microns away from us, which is smaller than your own heartbeat, but will never be reached by normal means. There's also the interesting thought that branes could still crash into each other. If another brane crashed into ours again, it might start a new Big Bang in space, which could restart or even destroy our universe. These aren't just ideas from science fiction, they're theoretically possible outcomes of string theory. It's hard to believe in brane cosmology because we can't see extra dimensions or other branes directly yet. But experts are looking for proof that can't be seen directly. As an example, it is possible for gravitational waves to carry echoes of how they interact with other branes. Small changes in the cosmic microwave background could be signs of brane crashes that have happened in the past. Particle accelerator studies like the ones at CERN might find proof of extra dimensions or particles escaping into the mass. What does it say about the universe's edge? The idea of an edge is changed in brane cosmology. There is no wall or black hole at the end of our world. Instead, it's like a sheet floating in a deeper reality, with no edges in our own. If you kept going in the same direction, you would always be on the brane. If it loops back on itself, you might go around it, but you would never leave it. You would have to go into a whole different plane to go beyond, which may not be possible for beings like us. Unless, and this is a very big if, there are quantum tubes or holes in space-time where the branes touch. For now, these are just guesses, but the idea is interesting for both science fiction and theory talks. In what part of the universe does the fabric of our universe thin out? Could we see or even touch another world there? Bubble universes. What if our universe is just one bubble in a big ocean of space? What if there are a million more popping up all the time? This is the amazing idea behind bubble universes, which comes from the theory of endless inflation. It changes how we think about what might be out there beyond what we can see in the universe. It would mean that our universe is not the only one out there, and that the huge reality we experience is just a small part of a multiverse that is so much bigger than we can imagine. First, let's talk about cosmic inflation, which was a very short but very explosive event that happened a very small part of a second after the Big Bang. The idea of inflation says that space didn't just get bigger, it grew bigger faster than the speed of light. This smoothed out any bumps in the space-time and explains why the universe looks so uniform now. A lot of people agree with this idea, and studies of the cosmic microwave background greatly support it. But some ideas about inflation, especially those that come from quantum field theory, say it never really stopped. Instead, endless inflation says that inflation stopped in some places, but is still going on in others. These quieter areas where inflation stops make bubble universes, which are separate areas of space where the fast expansion slows down and makes room for galaxies, matter, and life. It's like a bubble around us. But there could be a huge number more. Physics rules could be different in each bubble world. There could be different particles, forces, and even dimensions. In some, the pull of gravity might be higher, stars might not form, or atoms might not stick together. Conditions in some places might be even better for living things than here. And what's even stranger is that they might always be out of reach, growing farther away than light, and losing their edges as quickly as they appear. So how do these bubbles form? The mechanism comes from the quantum fluctuations of a hypothetical field called the inflaton field, which drives inflation. Think of the inflaton field like a sea of energy. Occasionally, a fluctuation occurs that's strong enough to knock a region of space into a lower energy state. This transition causes inflation to stop locally, forming a bubble. Meanwhile, the rest of the field continues inflating, producing more and more bubbles over time. The process is self-replicating, like cosmic popcorn popping eternally. This gives rise to the multiverse, not in the science fiction sense of parallel timelines, but in the physical sense of a landscape of bubble universes, each with its own version of reality. But will we ever be able to see these other worlds? This is where things get tricky. Space is expanding faster and faster, so other bubbles are usually far away from us, divided by large areas of space that are still expanding. They are moving away faster than light can travel because of inflation, so we can't see them directly. However, some scientists think that if two bubbles came together and hit each other, it might leave a tiny circular mark on the cosmic microwave background, like a stone hitting water and making a splash. As of now, no such clear trace has been found. Some strange things, like the enigmatic cold spot in the CMB, have led people to think that they might be the marks left by bubbles crashing into each other in the past. Bubble worlds have philosophical and even spiritual effects that go beyond the realm of science. In a multiverse that goes on forever, every option takes place somewhere. In a different world, Earth might have formed in a different path, and dinosaurs might not have died out. One where the laws of nature are just a hair different, which is small enough to stop all life, and another where advanced civilizations thrived a very long time before ours. There may even be copies of you living in boxes that are similar to yours, but a little different from them, because they were made by rolling different quantum dice. Some physicists agree with this thought and say that the multiverse is the reason why our world seems to be so good for life, stars, and planets. No, the world wasn't made just for us. We just live in a bubble where things are perfect, because no one else could survive in the billions of places where they aren't. But some people fight back. They say that the multiverse might not be able to be proven wrong because it can't be tested, which means it's not part of standard science. Can the idea ever be proven if we can never see another bubble? Proof is still being gathered in a roundabout way. Eternal inflation comes from known science. It doesn't need any strange theories. And if other expectations of inflation line up with what we see, like how the CMB is structured, it gives the overall framework more weight. It's even been said that the flatness and uniformity of our world are best described by the idea that it's just one bubble among many. What does this mean for the edge of the universe? The edge in the bubble universe model is not a spot in space, but the edge of inflation. Our universe came from a bubble where inflation stopped, surrounded by a storm of space that was always expanding. It would be like trying to reach the edge while swimming uphill in a river that moves faster as you go. You can't get there, and the water never stops moving. But in theory, if a way were found to punch through the inflating barrier, a kind of quantum tunneling into another bubble, we might experience a universe with utterly foreign laws. Most likely, Such a journey would be instantly fatal, as the energies involved would tear apart any familiar matter. But the idea remains one of the boldest frontiers in cosmology. The ekpyrotic universe. Think about the universe as a whole, with galaxies, stars, planets, and everything else, not coming into being in a fiery explosion from a single point, but through a clash of galaxies. A planned, slow, but unbelievably strong crash between two huge S+ pace sheets. This is the idea behind the ekpyrotic universe, which is a very different explanation from the usual Big Bang one. The term ekpyrotic comes from the ancient Greek word ekpyrosis, meaning conflagration or out of fire. It refers to a recurring cosmic event described by the Stoic philosophers, where the universe cyclically burns and is reborn. In modern cosmology, the term has been repurposed to describe a theory rooted in string theory and higher dimensional physics, one where our universe is not the product of a single point of origin, but of the clash between two four-dimensional branes. Brane cosmology, which is an extension of string theory, says that the universe might be a three-dimensional brane, short for membrane, floating in a four-dimensional area known as the bulk. Imagine our world as a huge dark sheet of space that is stretched out in a cosmic dimension with other sheets of space. In the ekpyrotic model, there is at least one other brane that runs parallel to ours and is split from it by an extra spatial dimension. This extra dimension is so small that we can't even see it, but it's there. It's possible that this other brane has its own world, physics rules, and kind of space and time. After that, it moves. The two branes move toward each other over very long periods of time due to gravity pull or quantum effects. When they hit each other, the kinetic energy is turned into matter and radiation, which is what we think of as the Big Bang. The catch is that this model doesn't start with a singularity. There is no point with an infinitely small density. The Big Bang is now just a transition, a time of extreme energy release caused by a brane collision. The universe doesn't just appear out of thin air. It grows from a structure that was already there and has been getting ready for its next move. The branes bounce apart after the crash. As in normal astronomy, the energy fades away, space grows, and galaxies form. But in the end, the branes slow down, turn around, and start to move back toward each other. This leads to another crash, a new world, and the Big Bang. This will never end. This is the cyclic form of the ekpyrotic model, which says that the world is born only once, and then born again and again. Each cycle could last up to a quadrillion years. After each bang, everything starts over, with new physics, new stars, and maybe even new kinds of life. The universe stops being a straight line of events and starts to have a moving, living beat. One of the strongest motivations for the ekpyrotic model is that it provides solutions to deep cosmological puzzles. The flatness problem. Why is the geometry of space so close to perfectly flat? The horizon problem. Why does the universe appear so uniform, even in regions that seemingly couldn't have communicated with each other? The singularity problem. How can physics explain a beginning from nothing if singularities break all known laws? One way that eternal inflation solves these questions is by positing an exponential growth that evens things out. However, the ekpyrotic model suggests a different way. It says that the slow, ordered contraction that happens before a brane crash can make conditions that are smooth, flat, and uniform, which naturally lead to our universe. There is no need for an inflationary blast. It gets even more exciting with physics. This model includes 11-dimensional space, quantum fields, and the behavior of branes because it is connected to M theory, which is one of the best ways to bring together quantum physics and general relativity. This theory says that each brane is like a blank surface that a universe can paint on its own. There is energy and fields in the area between branes, which can change the result of each new cosmic cycle. Now, what would it mean to exist between brane collisions? From a physical standpoint, we might experience little difference. Life on Earth, galaxies, cosmic structures, They form and evolve just like in standard cosmology. But over immense time, the universe would begin to slow, stop expanding, and contract ever so gently. The stars would die out. Space would become cold and dark. And then, deep in this dark epoch, the brains would once again come together. Bang! A new universe, fresh and hot and teeming with possibilities. For me, the most interesting thing about the ekpyrotic model is that it makes statements that are different from inflation. For instance, it says that the gravity wave background, which is the deep hum of the early universe, should be a lot less loud than inflation says it should be. It also shows small trends in the changes in the temperature of the cosmic microwave background, CMB, which might make it different from other models. These ideas might be proven or disproved by future tests, like ones that measure the CMB or gravitational waves with more accuracy. Many old beliefs, from Hinduism's breathing Brahman to the Stoics' idea of endless return, are deeply connected to the idea that the world is eternal, cyclical, and renewing. It changes how we think about cosmic death, not as an end, but as a disguised beginning. From this point of view, the edge of the world is neither a physical limit nor the end of time. It's the line between cycles, the line between times. If you could stand on the edge of two brain collisions, you would be in the middle of two different times and see one world end and the other begin. Quantum tunneling into new realms. Imagine that you are standing on the edge of everything, time, space, and energy, and then all of a sudden you feel like you are not there. It was not erased or destroyed, but written over, not ending, but starting somewhere else. This is the reality that quantum tunneling on a cosmic scale describes. It's a strange and confusing event that lets particles cross barriers they shouldn't be able to, going against classical laws as if they were led by secret odds. Use that for the whole universe now. When it comes to the quantum level, particles don't act like balls on a table. They don't have a clear place because they live in a fog of options. Particles can sometimes appear on the other side of an energy barrier when everything else seems to say impossible. This is called quantum tunneling. It's how the sun burns, how radioactive matter breaks down, and how life itself moves forward one very unlikely atomic leap at a time. Now scale that up. What if the universe itself could tunnel, not through space, but through states of reality? Some physicists believe that what we perceive as our universe, with its familiar laws of physics, constants, particles, and forces, is just one configuration in a vast landscape of possible universes. In string theory, this is referred to as the string landscape, a nearly infinite array of vacuum states, each with its own set of physical laws. Our universe, then, is like a marble resting in one valley among many peaks and troughs. According to quantum field theory, the vacuum isn't truly empty. It's a seething, fluctuating sea of energy and potential. And in this sea, it's possible for a region of space to suddenly tunnel from one vacuum state to another, from a false vacuum, a local minimum, to a true vacuum, a lower energy state. It's the cosmic equivalent of the ground beneath our feet suddenly giving way, not into a hole, but into another kind of existence entirely. This event is called vacuum decay, and while it sounds apocalyptic, it's fundamentally a shift in the fabric of the universe itself. The bubble of true vacuum would expand at the speed of light, replacing the old vacuum and everything within it with a new one. The laws of physics, the constants of nature, even the number of dimensions could change. Space and time might reconfigure. Matter could be erased or reshaped. If quantum tunneling between vacuum states is real, then the idea of the universe's edge is more like a covering between different worlds. We could be just one bubble in a huge froth of worlds, each one born from a quantum fluctuation and separated by lines we can never cross, unless the universe changes the rules. This means a lot of things. It means, among other things, that the world is metastable. There isn't a very low energy level, but it's stable enough for now. But quantum physics says that tunneling could happen if there is enough time. This is not science fiction. It's a real projection based on what we know about astronomy and field theory right now. Based on the Higgs field and the known masses of fundamental particles, some scientists even think we can guess how likely it is that such an event will happen. If a vacuum decay occurred, the bubble of new reality would expand at light speed. There would be no warning, no time to observe, no time to react. It would be, in every meaningful sense, instantaneous. But rather than being a cold end, it might be the beginning of something else. Inside the bubble, a new universe could emerge, one with different laws, different constants, maybe even different forms of matter or life. So what lies outside the edge of the universe? Maybe it's not just space, maybe it's probability, a rolling dice of quantum outcomes where entire universes shift, blink, and shimmer into being. Maybe we live on a ledge of potential, perched between one vacuum and another, oblivious to the invisible thresholds all around us. This makes me think of a multiverse that is both scary and beautiful. It's not made up of different spaces, but of options that are close together, like musical notes ready to be played. If quantum tunneling is real in the universe, then the edge of the universe isn't a wall or a blank. It's a way to get to other worlds. Not traveled with ships or probes, but with time and chance. Even more interesting, some ideas say that tunneling might not only fill in empty space, but it could also make new bubbles. This is like the idea behind endless inflation, which says that every tunneling event creates a new world. Each bubble grows and changes on its own. This is the bubble we live in. There could be a huge number more, split not by space but by energy state and cause and effect. What if our own universe was born this way? In this view, the Big Bang wasn't the beginning of everything, but merely the birth of our particular vacuum bubble, emerging from a parent state through quantum tunneling. We didn't arise from nothing, but from a higher energy realm that spilled into being, cooled, and formed everything we see. And what about the edges of this bubble? They're unreachable. They expand at light speed, just like the outer limits of our observable universe. But unlike the edge of a balloon that we could someday catch up with, these edges aren't physical locations. They're the transition zone between two distinct realities. The outside is not space we can reach, but a different physics altogether. But it does bring up an interesting question. Could we ever pick up the weak sound of tunneling? Could we see the mark of a vacuum bubble crashing into another? It could be in the form of faint scars on the cosmic microwave background, or strange changes in energy and shape. There are experts who think it's possible. They have been looking for clues, like hints of curves, cold spots that can't be explained, and sudden changes in temperature or density. The door is still open, even though nothing solid has been found yet. Some of the most important things in the world stay hidden until we're ready to ask the right question. And even if we never see the tunneling happen, its implications linger. They whisper of a cosmos in flux, a reality where what exists is only temporary, a fleeting chapter in a much larger book. Quantum tunneling isn't just a quirk of particles. It may be the engine of cosmic renewal, the spark that lights new realms when old ones fall away. Dark flow. Even though it's not something we can see or touch with our tools, there is something out there that pulls on our universe like a secret current under a huge ocean. This unseen force is called dark flow, and its presence is still hotly debated. However, it is one of the most tantalizing signs that there might be something bigger, stranger, and completely unexpected beyond what we can see. The story begins with the cosmic microwave background, CMB, the ancient faint afterglow of the Big Bang. This radiation stretches across the sky and acts like a photograph of the universe when it was just 380,000 years old. It is nearly uniform in every direction, but with slight variations, temperature fluctuations, and hot or cold spots that provide clues about the large-scale structure of the cosmos. Let's say you are a scientist mapping this background in space with satellites like WMAP or Planck. You notice that galaxy clusters, which are huge groups of matter that hold hundreds or even thousands of galaxies, aren't moving the way you'd think they would. They're not just moving in any way. No matter where they are, they all look like they're moving at the same speed, up to 600 to 1,000 kilometers per second, toward a certain area of the sky. There is nothing in the visible world that lines up with this trend. It's not like the gravity pull of other superclusters that we know of. If you look at it on a cosmic scale, it looks like space itself is being pulled by something beyond the cosmic limit. This is dark flow. The term was coined by scientists attempting to explain why these galaxy clusters appeared to be streaming toward a patch of sky in the direction of the constellation Centaurus. The measurements were based on a technique involving the Sunyaev-Zeldovich effect, where photons from the CMB gain energy as they pass through hot gas in galaxy clusters. By studying these subtle shifts, astronomers could estimate the velocity of these clusters, and what they found didn't fit with the standard model of cosmology. The idea is simple but startling. Massive structures that exist outside our observable universe might be exerting gravitational influence on the regions we can see. If true, that would mean our observable universe, the 93 billion light-years across that we can currently detect, is just a bubble in a vastly larger reality, and that immense concentrations of mass reside beyond our horizon, dragging entire galactic neighborhoods in their direction. Take a moment to think about that. Superstructures, which are impossibly huge groups of matter that could be whole other worlds, might be pulling on ours. Even though we can't see or touch them, the small moves of matter on cosmic scales may give us a hint of their presence, but not all of them agree. People have looked closely at the idea of dark flow. There are some experts who say the data might be wrong, or the result is not statistically significant. Later searches with the Planck telescope did not find the same signal that the WMAP data had shown. This caused a split in the scientific community. One group believes dark flow is proof of physics beyond the standard model, possibly proof of a universe or higher dimensional gravity. The other group believes it is just a measurement error, a cosmic mirage caused by noise or wrong interpretation. It forces us to confront the possibility that gravitational information is not constrained by the speed of light in the same way electromagnetic signals are. Gravity propagates at light speed, yes, but if something truly enormous lies beyond our cosmic edge, its gravitational influence may still be felt across the ages. In that sense, gravity becomes a kind of messenger from the unknown, whispering of the unseen in the way starlight cannot. The anisotropies in the cosmic microwave background, including the axis of evil, a strange alignment in the large-scale structure of the CMB, suggest that something outside our observable bubble might be shaping the internal patterns of our universe. Dark flow, if real, would fit into this family of anomalies, clues to a deeper truth, scratched onto the sky by an unseen hand. In some inflationary multiverse models, bubble universes can crash into each other, and their effects could spread through each other like waves merging in a cosmic pond. This kind of collision might leave scars, gravitational shears, flows of matter, and patterns in the CMB that don't follow random statistical noise. In this case, dark flow wouldn't just be a hint at another universe, it might be direct proof of our universe crashing into another. Like tectonic plates grinding in the void, the boundary between universes could create strange effects, changing the path of matter on scales that are too big to understand. But we must tread carefully. The observable universe is the largest thing we can study directly. Everything beyond that is inference, speculation, extrapolation. And yet, science lives in the realm of the inferred. Every theory begins with a mystery. Every breakthrough starts with a question. Why is that moving like that? And the question, why are these clusters moving together toward a place that can't be seen, is still open. Dark flow shows us that the universe is more than just very big. It could be the pull of unknown giant structures, the whisper of another universe, or a mirage written into our measures. It's not right, and the lines we draw between what we know and what we don't know, what is real and what is imagined, are often much thinner than we think. The cold spot enigma. High above us, in the faint glow of the early universe, there is a puzzle that is so small, that it was almost missed. It is also so puzzling that it keeps putting our most trusted models of the universe to the test. This strange area in the cosmic microwave background, CMB, is called the cold spot. It covers a huge area of sky in the constellation Eridanus and is surprisingly cold. But this isn't just an interesting piece of astrophysics. It could be the mark of something from another world. Before we can understand how important this mystery is, we need to know what the CMB is. When we look up at the microwave sky, we see radiation that comes from about 380,000 years after the Big Bang. This is when the universe got cool enough for atoms to form and photons could move easily. From then on, this light has been traveling, slowly turning red as space expands. These days, it paints the sky with almost perfect regularity, a kind of cosmic wallpaper, with tiny temperature changes that show how galaxies grow. In 2004, astronomers using NASA's Wilkinson Microwave Anisotropy Probe, WMAP, noticed a strange feature: a large region roughly 5 to 10 degrees across that was significantly colder than expected. This cold spot wasn't just slightly off, it was anomalously low in temperature compared to its surroundings. Later, the Planck satellite confirmed it. The data wasn't a fluke. There really is a patch of the sky that defies statistical expectations. Then, what could make it happen? The first idea was pretty reasonable. Maybe the cold spot was a supervoid, which is a huge area of space with a lot less matter than usual. On a very large scale, galaxies are made up of webs of filaments, clusters, and empty spaces. The integrated Sachs-Wolf effect is a gravity redshifting process that can happen to light moving through these holes. This is where the curve of space-time changes the energy of photons in very small ways. If there is a supervoid, this effect might make CMB photons lose energy, making them look colder when they get to us. This explanation held promise. In 2015, observations using the Dark Energy Survey suggested that a vast underdense region, a void hundreds of millions of light-years across, could exist in the cold spot's direction. But further studies cast doubt. The void wasn't quite big enough. The temperature difference of the cold spot was too extreme. Statistically, it remained an outlier, something not easily explained by current structure formation models. As a result, the cold spot went from being a normal, if rare, event to a cosmic puzzle. A theory that is getting more attention is that the cold spot might be a scar from a clash between bubble worlds in a multiverse. Some models of inflation say that our universe is just one bubble in a foam of space that is always getting bigger. These bubbles might sometimes hit each other, like soap bubbles in a sink. If that happened very early in the past of the universe, the impact might have left a mark on the CMB, either by changing its temperature or shape. The cold spot could be such an imprint, a ghost of another world that quickly crossed paths with ours, before drifting away out of reach but never really gone. A different universe with different physical rules may have touched ours at some point in the very distant past. The other universe is beyond our causal reach, so we wouldn't be able to see it directly. However, we might be able to pick up the aftershock in the cosmic microwave background, a small area of cold, an itch in the big picture of everything. This situation may seem impossible, but it fits easily with ideas like eternal inflation, which says that space keeps growing forever in some places while pocket universes form and solidify from time to time. Fundamental constants may have different amounts in each pocket. Some people may not like matter, others might have life in them. From this point of view, the cold spot is not just a chance drop in temperature, it's a warning from beyond the stars, written in the light from the Big Bang. But let's step back. The cold spot remains controversial. Some scientists caution against leaping to exotic conclusions. Our universe is big, really big, and rare things do happen in large data sets. Even if the probability of such a cold region is low, it might just be cosmic variance, a statistical fluke, a roll of the dice in the cosmic lottery. Could there be other subtler anomalies like it, clues sprinkled across the CMB that point to physics beyond the standard model? Some researchers are now using machine learning to search for patterns in the background noise, looking for other hints of bubble collisions or topological defects. Others are scanning for non-Gaussianities, deviations from the expected statistical distribution in the CMB, which might signal the presence of new physics. Philosophers and cosmologists are both thinking about what this means at the same time. Why is the cold spot a multiverse bruise? What does that mean for the place of our universe in the big picture of the universe? Is our world just one of many that float through an endless sea of possibilities? Do the cold spots make us think that we are not alone, not just in life, but in everything? But maybe the cold spot isn't a structure in space, but a structure in our ideas, a hole in the way we think about how the universe started. It could be a sign that inflationary theory is wrong, or that our knowledge of quantum gravity is thin. One thing is still clear: the cold spot will last. It hasn't been thrown out or fully explained. The radio sky is empty and quiet, as if it doesn't want us to try to understand it. It makes us question what we think we know and asks us to picture what we don't know, like a word from the edge of our understanding. Unobservable galaxies. We can see galaxies everywhere in the universe. Each one is a huge city made up of stars, gas, dust, and dark matter, spread out like bright islands across the universe. There are hundreds of billions of galaxies that we can see, and each one has billions of stars. But what we see may not even be a small part of what's out there. Galaxies that we can't see drift through space, forever hidden by time and distance. The reason for their invisibility lies in one fundamental limitation. Light has a speed limit, and the universe has an age. But beyond this bubble, there may be vast realms of galaxies we'll never see. Not now, not ever. These are not hypothetical galaxies. They are as real as the Milky Way. They could contain stars just like our Sun, planets just like Earth, and even intelligent life wandering about the cosmos just as we do. But the space between us and them is expanding faster than light can travel. As a result, their light will never reach us. These galaxies have slipped over our cosmic horizon, a line drawn not in space but in time. This limit is also not set in stone. Each second that goes by, light from a little farther away gets to us. As our knowledge of the universe grows, so does the space between us and those galaxies that are getting farther away. Rather, the number of galaxies we can see will decrease in the far future because the universe is expanding faster than ever. This is caused by something we term dark energy. It's kind of like being on a big plane and seeing campfires off in the distance. At first, as the smoke lifts, more and more can be seen. But over time, those campfires start to go out and disappear into the night, driven away by a wind you can't see. In the big picture, that's what's going on. How many galaxies are out there beyond our sight? The Hubble Space Telescope and more recently the James Webb Space Telescope, JWST, have provided astonishingly deep field images of tiny patches of sky, revealing thousands of galaxies in areas no bigger than a grain of sand held at arm's length. By extrapolating these deep field counts across the sky, astronomers estimate the observable universe contains around 2 trillion galaxies, but that's just the visible slice. Many astrophysicists suspect the total number of galaxies, including those we'll never observe, may be infinite, or at the very least so vast as to be effectively uncountable. Some models suggest that the unobservable universe could be hundreds or even thousands of times larger than what we can see. If true, then for every galaxy we know, there may be hundreds or thousands more, floating in unreachable realms. Do the rules of physics apply to both? We think that the unobservable world should follow the same physical rules as ours, since they both came from the same Big Bang. But if we look at inflationary multiverse models, some of those galaxies might be in different bubbles in the universe, where the laws of physics are different. These bubbles might have different gravity levels, particle masses, and even numbers of dimensions. This has very important effects. There may be galaxies out there that we can't see where the stars aren't made of hydrogen and helium, but of strange particles. there may be places where gravity is a little stronger, which would make stars burn out faster and galaxies fall apart faster. Some places might not even be possible for life as we know it. On the other hand, there may be galaxies remarkably like our own, complete with spiral arms, supernova, planetary systems, and perhaps civilizations. Could those civilizations ever know of us? Almost certainly not. The gap between us grows faster than light can close it. We are, in a very real sense, cut off. This isolation may seem tragic, but it's also awe-inspiring, because in every direction, just past the edge of the observable, are countless worlds we'll never meet, and skies we'll never map. The cosmic darkness isn't empty. It's overflowing with hidden complexity. And just like there are galaxies that can't be seen, many other galaxies can't see us either. People who look into a universe that is growing as quickly as ours have their own cosmic boundary or small piece of the universe. We live in one of these slices. For a being in a world 50 billion light-years away, we might already be too far away to reach, even in theory. In a very deep way, this makes you humble. At first glance, our part of the universe seems very big and full of things, but it could only be a small piece in a much bigger and more complicated puzzle that we can't even begin to piece together with our tools. Some scientists are hoping that future studies will give us hints about these galaxies that are hidden. It's possible that gravity waves, cosmic neutrino backgrounds, or small changes in the rates of expansion will tell stories from the edge of what we can see. One day, maybe we'll be able to see the total mark of galaxies that we can't see by how they pull on things we can see. But for now, all we can do is guess and infer. That may be why they are so strong. The galaxies that can't be seen are not only far away and dark, but they are also the very essence of wonder. They tell us that we are not here to take over the world, but to be humble and amazed by it. That there are more stars, stories, and questions behind every part of the night sky. The unknown mass is made up of them. Those are the galaxies past the edge. Even though we'll never get to them, they change the way we see the universe, not by shining light on it, but by being there. The limits of cosmic light. Light is our window to the universe. Every galaxy, star, and planet we know because of light. It travels across space and time to carry ancient messages from distant corners of the cosmos, revealing the history of stars, the birth of galaxies, and even the echoes of the Big Bang itself. But light, as miraculous as it is, has its limits. And those limits define the edges of what we can ever hope to see. To understand what exists outside the edge of the universe, we must first understand the limitations of light, because our entire view of the universe is ultimately constrained by how far and how fast light can travel. The first and perhaps most famous is the cosmic microwave background, CMB, the oldest light we can see. It comes from about 380,000 years after the Big Bang, a time when the universe had cooled enough for electrons and protons to combine into neutral atoms, allowing photons to travel freely through space. Before that era, the universe was opaque, a blinding hot plasma that scattered light constantly, much like the inside of a star. This makes the CMB the limit of electromagnetic visibility. No matter how good our telescopes become, no matter how long we wait, we will never see light from before the CMB, because no light from that earlier epoch was free to travel. It's like trying to see inside a star by looking at its surface. There's a limit beyond which visibility ends. Cosmologists call the time period after the CMB the cosmic dark ages. It is the time between the last scattering of photons, when the CMB was released, and the start of star formation. At this point in time, the universe didn't have any light that could be seen, or that was close to infrared. It was a vast, dark, and quiet space full of cool gas and the beginnings of galaxies. The first stars and galaxies were formed when gravity collapse started, what is called cosmic reionization. This is the process by which starlight lit up the universe again, ending the Dark Ages. The James Webb Space Telescope will look back over 13 billion years to find the first bright objects and study this early period. However, not even it can see into the pre-stellar darkness before reionization, or past the CMB. What happens if we try to go even further back? To learn about the first 380,000 years of the universe, or even the first fractions of a second after the Big Bang, we need to use non-electromagnetic messengers. Light won't help us there. We need to use gravitational waves and cosmic neutrinos, which aren't limited in the same ways that photons are. Einstein predicted gravitational waves would exist in space-time, and they did. In theory, gravitational waves could pass through the hot, dense early universe where light couldn't. If we could find primordial gravitational waves, we might be able to see the universe as it was right after inflation. The idea that it grew exponentially in the first few hundredths of a second. However, these waves are very weak and hard to find, and so far we've only seen them from relatively recent events like black hole mergers. Then there's the cosmic neutrino background, ghostly relics of the Big Bang that decoupled from matter just a second after the universe began. These neutrinos are incredibly abundant, but because they interact so weakly with matter, they are nearly impossible to detect. Still, they're out there, forming a silent, invisible boundary even older than the CMB. If we could learn to see them, we could peel back the curtain of time even further. And here lies the paradox. The earliest moments of the universe are also the most shrouded in darkness. The closer we get to the beginning, the more our traditional observational tools, like light, break down. The physics of that epoch involves energy scales and conditions that we simply can't reproduce and in many cases can't yet describe with certainty. Our best models, quantum field theory, general relativity, string theory, strain under the pressure of those early instants. Even worse, dark energy speeds up the growth of the universe as we move closer to the edge. Even though they are billions of light years away, some galaxies are moving away faster than light. This isn't because the galaxies are moving through space, but because space is getting longer. So, no matter how long we wait, the light coming from those galaxies today will never reach us. This is not a violation of special relativity. Special relativity forbids objects from moving through space faster than light, but space itself can expand as rapidly as it wants. In fact, more and more of the universe is becoming invisible every second. In the far future, only the galaxies gravitationally bound to us, like those in our local group, will remain visible. The rest will fade away, forever beyond the reach of light. Which means that the answer to the question, what is outside the edge of the universe, is light. There may be no end to the world. Light can only go so far, though. The edge is not a wall or a real line. It's the edge of what the light can show us. After it, there is darkness. Not empty space, though. There may still be stars burning, galaxies growing, and whole civilizations staring into the night sky without seeing us, just as we don't see them. They are not reachable by photons and can't be traced through light's past. And their light will always be beyond the edge unless we find new ways to see the universe, like using neutrinos, gravity waves, or information sources we don't know about yet. The boundaries of cosmic light aren't just about science in the end. They're about how you see things. They help us remember that what we see is only a small part of the whole. That even though the world is made of light, there are places where it is dark. This isn't because there is nothing there, but because the light hasn't come yet. Is there an anti-universe? The idea of an anti-universe comes from scientists trying to figure out some of the biggest puzzles in modern physics, especially those that have to do with symmetry. The idea behind physics is that certain patterns should hold true in both space and time. What does CPT stand for? It stands for charge, parity, and time. If we do three things at the same time, reverse the charge of all particles, making matter into antimatter, flip their spatial dimensions, making a mirror image or parity, and go back in time, the rules of physics should stay the same. A lot of physics rules follow this CPT symmetry. The basic way particles behave doesn't change when you use all three transforms at the same time. The universe may follow this pattern, but only locally. What about on a larger scale? When the anti-universe theory comes in, it helps explain this. Some cosmologists think that the Big Bang wasn't the start of time, but rather a point of change, a time when everything was perfectly balanced. Our world, which is growing forward in time, is on one side of this line. On the other side, a world that grows backwards in time, like a mirror, where antimatter rules and all physical processes happen backwards. This idea is not just philosophical musing, it's mathematically grounded in attempts to explain anomalies in particle physics. For instance, we know that our universe contains far more matter than antimatter, a fact that remains one of the great unsolved puzzles of cosmology. Theoretically, the Big Bang should have produced equal amounts of both. So where did all the antimatter go? One answer is that it didn't go anywhere. It just exists somewhere else, in the anti-universe. This mirror realm wouldn't just have antimatter in it, it would also have time turned around, which is similar to anti-causality. From our point of view, things would happen there in a way that looks like a timeline going from the future to the past. From that universe's point of view, though, they are going forward at their own pace. In the same way that we feel chaos rising, they would too, but in the opposite order. It's hard to think about this without running into conflicts. People in the anti-universe would remember the past and look forward to the future, right? How would their physics feel compared to ours? It's possible that the answer is yes. All of their processes, from nuclear fusion to organic growth, would happen at the same time in their world, so their experience would be the same as ours. They wouldn't see themselves that way at all. They would think we were weird. The most exciting thought is that some cosmic signs might point to the existence of a mirror world like this. Neutrinos, which are ghostly particles that don't interact with matter very often, could be a sign. According to the standard model of physics, neutrinos come in 3 different types. All of them are left-handed, which means their spin direction is opposite to their speed. This difference in handedness is strange because most particles come in both left and right-handed forms. This imbalance could be fixed by the anti-universe model, which says that the right-handed neutrinos, which we have never seen, are actually from the mirror universe, just like the left-handed ones are from ours. If this is true, it would not only solve the symmetry puzzle, but it would also help us learn more about dark matter, which some scientists think might be made up of these right-handed neutrinos. But what's even more interesting is the idea that our universe and the anti-universe may have both come from the same event that happened at the same time. The Big Bang is not a place where physics stops working. Instead, it is like the middle of a bow tie. It is where 2 worlds meet and start moving in different directions in time. From this point of view, time doesn't move in a straight line. What we think of as forward is really just one part of a bigger picture. The anti-universe, which we can't see or reach, may be growing and changing in perfect order, with its own galaxies spreading, stars burning, and maybe even life developing in a place we will never be able to reach. Could we ever detect this anti-universe? Perhaps not directly, but some cosmologists believe that subtle traces of this mirror reality could be hidden in the cosmic microwave background. Tiny anomalies or unexpected patterns in the CMB might be interpreted as echoes of the symmetry across the Big Bang boundary. There is even speculation that certain gravitational waves, ripples in the fabric of space-time, could carry signatures from both sides of the temporal divide. But these ideas haven't been proven yet. The anti-universe is still just a theory, a mathematical possibility that needs to be proven by experiments. Our equations look better and are more balanced with this answer, but we don't have direct proof of it yet, so it's still just a guess. If there is such a thing as an anti-universe, then the Big Bang wasn't a unique start, but rather a point of birth that is mirror symmetric. We are not the only thing that came from the beginning of the universe. We are only one part of a perfectly balanced system. That being said, we might never trade light or matter with this other universe, but the symmetry could change neutrinos, dark matter, chaos, and even the direction of time itself. Gravitational waves from beyond. A wave came to Earth in 2015. The wave wasn't made of light or sound, it was a gravity wave, which is a distortion in the very structure of space and time. It was the first direct discovery of these elusive waves, which were made when two black holes collide more than 1 billion light-years away. This confirmed Einstein's statement from 100 years ago. Gravitational waves are not made up of particles. They are ripples in space-time that are caused by huge objects moving quickly, like neutron stars combining or black holes spinning. Light can be spread or absorbed, but gravitational waves almost never get blocked when they go through matter. They carry knowledge not about the outside of cosmic events, but about the very centers of them. This includes the times when stars collide, black holes merge, and the structure of space is violently remade. Now think about this. If gravitational waves can reach us from such violent crashes, could they also bring signs from other universes that we can see? This is what some experts think. If there are huge structures or events in the universe beyond our cosmic horizon, which is the edge set by how far light has moved since the Big Bang, those things could still send out gravity waves. Gravitational waves might be able to reach us, but light from beyond that edge will never get here. There is a small chance that these waves could carry echoes from before recombination, from times when light was still stuck in the plasma of the newborn universe. They might even be from different regions of a bigger universe. Others think that gravitational waves might go through or around topological flaws in space-time, such as cosmic strings or domain walls, if they exist. These old pieces of the universe could shake or break, sending gravity signs over very long distances, maybe from worlds other than our own. If we could find these very low-frequency waves, they might give us our first look at what's beyond the edge of what we can see in the universe. Of course, discovery is the hard part. We can barely hear gravitational waves. LIGO was needed to record waves from inside our world because it can find distortions smaller than the width of a proton. To hear sounds from beyond, we would need even more sensitive tools, like the planned Laser Interferometer Space Antenna, LISA, for space, or maybe even completely new technologies we haven't thought of yet. The edge, according to general relativity. Physics works the way we see it in real life. We stay on the ground thanks to gravity, time moves forward, and space looks like it goes on forever. But physics doesn't work at the most extreme points of reality, like the center of a black hole, or the moment the Big Bang happened. In particular, Einstein's beautiful theory of general relativity, which has been our guide for more than 100 years, starts to fall apart. In general relativity, gravity is not seen as a force, but as the way that mass and energy bend space-time. It's what makes light bend around galaxies and planets go around stars. It says that time will slow down near very heavy things, that the universe will grow, and even that black holes will form. But the equations don't make sense at the edges of these statements, which are called singularities. A singularity is a point where density becomes infinite, and the curvature of space-time grows without bound. This isn't just a mathematical oddity, it signals the limits of our current understanding. General relativity cannot handle infinities. It can't describe what happens at the singularity, only approaching it. And that's crucial because if the universe has an edge, spatially, temporally, or conceptually, it may resemble such a singularity. Consider the Big Bang. We often picture it as a massive explosion from a central point, but that's misleading. The Big Bang wasn't an explosion in space, it was an expansion of space. What existed before it? General relativity has no answer. Its equations simply say, here lies a singularity, a beginning point where time and space, as we understand them, emerge. But why? From what? That's where relativity stops. Similarly, general relativity says that there will be a point inside a black hole, past the event horizon, where space-time falls into a singularity, but it doesn't say anything about what's there. Is it a pinprick with an infinitely high density? A hole that leads to another world? A way to get to another world? Our tools don't work in that area, so no one knows. Physicists believe that to truly understand the edges, the places where general relativity breaks down, we need a theory of quantum gravity, one that unites the smooth geometry of Einstein with the probabilistic nature of quantum mechanics. String theory, loop quantum gravity, and other candidates are attempting to bridge this gap, but none have succeeded definitively. Until then, the edges remain just out of reach. They are like a cosmic shoreline shrouded in mist, where the laws of physics we trust dissolve into paradox. General relativity is one of humanity's greatest achievements, but it leaves us with tantalizing questions. What lies beyond its domain? If the universe has an edge, perhaps it's not spatial, but epistemological, a boundary not of matter, but of understanding. The cosmic neutrino background. Before the first stars were born, and even before atoms were made, the universe was a sea of particles on fire. It was so hot and thick that light couldn't escape. Another type of particle, neutrinos, was born and set free at this time. These ghostly particles, which had almost no mass and didn't interact with anything much, slipped through the chaos and started their trip through space. They may hold secrets from the very beginning of time, even before light existed. The cosmic neutrino background, CVB, is a piece of history from the second after the Big Bang. That's about 380,000 years before photons of the cosmic microwave background, CMB, were released. This means that the C degree B could be a way to see a time that photons can't show. But finding these old neutrinos is like trying to hear a whisper in a storm. They don't interact with matter much. Every second, trillions of them pass through planets, stars, and us. Because the universe is expanding, the C12b has very little energy, making it even harder to find. Its neutrinos are colder and move more slowly than most we see. High-energy neutrino interactions are what make current detectors work, so they can't see them yet. Still, scientists are coming up with new ways to hear this very faint hum. Ptolemy, Princeton Tritium Observatory for Light, Early Universe, Massive Neutrino Yield, and other experiments try to find relic neutrinos by studying how they interact with tritium atoms in very small ways. If we are successful, we might be able to prove one of the last untested ideas about the Big Bang and see things that happened before we've ever seen them. The CVB is very interesting because it might be able to tell us about the world before light, before the CMB, and before any matter that we can see. Perhaps it will help us understand how matter and antimatter behaved, or whether unknown physics shaped the early universe. Neutrinos don't interact with anything very strongly, so they move through space and time almost unchanged. They are like messages from the beginning of the world. Assuming there was a before the Big Bang, some experts even think that leftover neutrinos might carry marks from that time. If the universe came from a cycle or a quantum shift in the past, these very small particles may still have signs of those events on them. The CVB is one of the most important targets in current astronomy, even though it is only a theory. Time before time. What was there before the Big Bang? For many years, this question was thought to be pointless and the last word in astronomy. We were told that the Big Bang was the start of time itself. To ask what came before was like to ask what lies north of the North Pole. Modern theoretical physics, on the other hand, doesn't like dead ends. Also, the idea of a time before time has been brought up in serious scientific conversations recently. This cutting-edge idea questions the very basis of causality and the past of the universe. Classical general relativity says that the Big Bang is a singularity, which is a place where space and time get so dense that the known rules of physics don't apply anymore. But these days, most scientists think that this singularity isn't a real thing, but rather a sign that we don't fully understand quantum gravity and where it should take over. In some theories of quantum cosmology, time doesn't start with the Big Bang. It just changes over time. The Hartle-Hawking no-boundary proposal is one of these ideas. In this plan, time is seen as a dimension that changes into space-like properties. near the beginning of the universe. The world doesn't have a clear start in this model. Instead, it ends in a curve that looks like the top of a dome. It doesn't have any sides, a hollow spot, or a real beginning. It's like a disk that slowly forms, with time moving from a quantum beginning that has no direction. Then, there are the bounce models, which are possible futures in which the universe shrunk in the past and then grew again. From these points of view, the Big Bang happened after the Big Crunch. There was no beginning of time 13.8 billion years ago. It either went backwards or forwards during a transitional period, guided by quantum rules we don't fully understand yet. In theory, these cycles could go on forever, making a universe that is always being born again and again, where time before the Big Bang is just time moving from one phase to the next. Some studies even say that time might not be basic but rather emergent. You could say that time could come from more basic quantum interactions, like how temperature comes from the movements of molecules. According to these ideas, time might not flow the way we think it does after a certain point in the history of the world. This means that there might be a place before time where things don't work the way we think they do. Not only does the idea of time before time push the limits of science, it changes them. It makes us think that our birth story isn't the start, but rather a part in something stranger, more circular, or more quantum than we thought. There might not be a void before the first tick of the universal clock. Instead, there might be a veil that new physics will one day lift. Exotic topologies. Most of us think of the universe as an endless grid, a three-dimensional stage that is always getting bigger where galaxies move apart, stars shine, and space itself grows. What if, though, the shape of the world is much stranger than we think? Come into the world of strange shapes, where space doesn't behave in a way that makes sense. In these models, the universe could loop, twist, fold, or wrap in ways that don't make sense in the real world. This would not only create new forms, but also new options for what lies beyond the edge. First, let's look at the torus world, which is already pretty strange, but has a lot of math behind it. Think about how the world looks like a big donut. In this kind of place, if you go far enough in one way, you'll end up back where you started, without ever turning around. This place doesn't have any edges. It's like the surface of a world, but in 3 dimensions. With this idea, beyond the edge is rethought as a structure with loops. You don't reach a wall, you do a cosmic lap. Then come even more curious constructs, Mobius strips, Klein bottles, and projective spaces. These are mathematical shapes where direction, orientation, and movement take on non-intuitive meanings. A Mobius strip has only one side and one edge. A Klein bottle, if extended to 3 dimensions, loops back through itself in a way that defies normal spatial logic. Applied to cosmology, such models suggest a universe where left and right might subtly blur, or where traveling up could gradually reorient you down. These are not merely thought experiments. They're geometries consistent with Einstein's theory of general relativity, given the right conditions. Hyperbolic geometries take things further still. In these models, space is curved in such a way that it spreads outward faster than flat space, creating infinite volume within finite bounds. Picture an endlessly branching coral reef, or a tree that sprouts new branches faster than light can cross them. In a hyperbolic universe, light rays that leave your position never reconverge, creating pockets of isolation and vast voids that mimic the structure of our own cosmic web. What's the point of these strange topologies? Because they change what the edge means. If the world curves, folds, or loops, then outside might just be a way to get back inside. The real limit might not be in space, but in structure, like a geometric cutoff that we don't know how to cross yet. It also means that 2 seemingly separate parts of the universe could be the same area linked by a wavy structure, like 2 ends of a folded piece of paper being taped together behind the scenes. There's also the intriguing chance that cosmic illusions are caused by strange layouts. The cold spot, the repeated galaxies, or the cosmic microwave background that we can't explain could be signs of a universe that folds or loops in ways we haven't found yet. If that's the case, the edge of the universe might be right behind you, bent by space. Wormholes and exits. At its core, a wormhole is a bridge. Einstein's field equations allow for a tunnel-like solution in spacetime. If you fold a piece of paper in half and then poke a pencil through it, the pencil moves straight through the paper instead of across it. This is the idea of a way to cut through spacetime faster than usual, avoiding normal lengths and possibly connecting places that are light years or even worlds apart. When it comes down to it, wormholes can be either intra-universal, within our own universe, or inter-universal, between worlds. Wormholes could lead to places far beyond the visible universe, or to worlds with completely different laws of physics if they exist and are stable enough. This puts them right in the group of exits, not just past the edge of what we can see, but past the edge of everything we think of as here. However, wormholes that can be crossed come with a lot of risks. The Einstein-Rosen bridge, which is the simplest type of wormhole that can be made from black hole math, is not stable enough to pass through. It falls apart too quickly for anything to get through. Theoretical physics says that we'd need strange matter with negative energy density to keep a wormhole stable. This is matter that doesn't follow the known rules of energy conservation. Small amounts of negative energy might be possible, as shown by quantum effects like the Casimir effect. But how this would work on a larger scale is still very much unknown. Then there's the matter of what caused what. If there are wormholes that can join 2 points in space or even in time, do paradoxes make sense? For example, could you come out of a tunnel before going into it? The chronology protection hypothesis is a theory that some scientists say quantum effects might self-correct to stop time travel problems. Still others think wormholes might work more like one-way gates, where once you go through them, you can't come back out. Yes, an exit, but not a return trip. People have also said that black holes could be one-way wormholes. Would you be able to get to the heart without becoming spaghetti? If not, could you come out somewhere else, or even when? Some ways of thinking about spinning black holes, Kerr black holes, imply this, with answers that point to structures inside them that lead to other universes. But once more, these are still very much guesswork and probably can't be crossed by any known material. Quantum wormholes are very small, short-lived links at the Planck scale. They may exist in a boiling foam of spacetime, even if real wormholes can't be traveled through. In theory, these mini wormholes could carry quantum information, pointing to a web of links we can't see beyond the horizon. Could the universe be made of secret shortcuts that change the structure of the universe without anyone knowing? If wormholes exist, and if we ever discover how to harness them, then the edge of our universe might not be a boundary, but a door. The universe as a simulation. What if the edge of the universe isn't a physical barrier, but a programmatic limit? What if everything, space, time, matter, consciousness, is unfolding inside something far more artificial than we imagine? Welcome to the provocative hypothesis that the universe may be a simulation. This idea, while speculative, has grown in popularity among physicists, philosophers, and tech thinkers alike. At its core is a simple question. If it's possible to simulate a universe, and civilizations can create countless such simulations, then how do we know we're not inside one? Philosopher Nick Bostrom laid out the argument in 2003, suggesting that at least one of the following must be true. 1. Advanced civilizations never reach the point of simulating universes. 2. They reach that point but choose not to simulate. Or 3. They do simulate, and we're likely living in one of those simulations. If 3 is true, then the edge of the universe may not be a horizon in space or time, but a boundary of processing power. Just like in video games where only the visible world is rendered, perhaps the universe generates detail only where and when it's observed. This would mean the unobservable universe isn't out there until we look, or try to. The simulation may have limits, and those limits could coincide with the cosmic horizon, where light hasn't had time to reach us. Beyond that, not rendered, not needed. Some scientists have looked for glitches, which are small mistakes in the universe code. It's possible that space might be broken up into pixels at the smallest scales, making a digital grid instead of a smooth line. Others think that high-energy cosmic rays might show anisotropies, which are preferred directions in space, which could lead to a computing base. There's also the quantum observer effect, which says that particles only choose a state when they are being watched. Could this be a type of planned strategy that changes reality based on how people interact with it? That would make every conscious experience a part of the user interface, UI, of the game. Yes, it's too much to say, but quantum physics already feels like software whose source code we can't quite read. In a simulated universe, the idea of an outside becomes radically different. Outside isn't more space, it's the higher dimensional reality where the simulation is running. The beings in that world, our programmers perhaps, would exist beyond everything we know, and their rules, motives, or physics may have no correlation to ours. Even time, as we experience it, may be a setting rather than a constant. Could we ever escape the simulation? Probably not in any traditional sense, but some thinkers propose that anomalous events, unexplainable coincidences, or sudden shifts in physical laws might hint at code changes, patches, so to speak. And in such a framework, asking what lies beyond the universe is akin to a character in a video game asking what's beyond the screen. Hidden higher dimensions. As you walk through your house, imagine finding a secret staircase hidden behind a bookcase. This staircase goes to a place you didn't know existed. Now picture this happening in space instead of your house. This is the crazy idea behind secret higher dimensions. There are realities all around us that are hidden so well that we can't see them. String theory and other similar models of basic physics say that the world is bigger than the 3 dimensions of space and time that we see every day. Instead, these ideas suggest 10 or even 11 dimensions, with the extra spatial dimensions being compacted or curled up so small that we can't see them. Calabi-Yau manifolds are complicated mathematical structures that are often used to show these squished dimensions. These are multidimensional geometric shapes that may be the building blocks of the particles and forces in our world. What does this mean for the universe's edge? Well, if these hidden dimensions are real, then the outside of the world we can see might not be in more space, but in places we can't go. Even more than not being able to go beyond the cosmic horizon, there may be whole ranges of directions where we physically cannot move. This is because our world is only a 3D slice of a much deeper reality. In this view, the universe could be like a sheet of paper floating in a vast higher dimensional space. We, the beings on the sheet, can move left, right, forward, or back, but never up or down into the larger space. And yet that space may be real. If we could somehow access it through a wormhole or a fluctuation in the fabric of space-time, we might discover that the edge of the universe isn't an end, but a fold. And on the other side, who knows? Perhaps another universe or a completely different realm of physics. Gravitational forces have been used in some studies to look for proof of higher dimensions. One idea for why gravity is weaker than the other fundamental forces is that it leaks into other dimensions. Experiments like the Large Hadron Collider have looked for signs of this kind of leaking, like energy that is missing or particles that behave in ways that aren't expected. But so far nothing conclusive has been found. If these extra dimensions are real, they might have something to do with how the world was formed and how the natural laws we observe work. They might even be able to bring general relativity and quantum mechanics together, which is the great grail of modern physics. It's possible that these higher dimensions aren't just curled up. Some of them could be wide open and link different universes, like roads between worlds. This means that what we think of as outside the universe might just be going sideways, in a place we can't point to, but that is real. The Big Bounce and cosmic recycling. What if the end of the world isn't really the end? What if it's just a breath between all the breathing that will ever happen? The Big Bounce theory says that our universe is just one in a never-ending pattern of birth, death, and rebirth. This is different from the common idea that the universe started with a Big Bang and is now growing all the time. This idea changes the way we think about what might be beyond the edge. The border is no longer a line that marks the end of space or time. It is now a path to another cosmic era. In a big crunch, the universe might fall apart due to its own gravity, like a phoenix rising from the ashes. It might then explode outward again in a new Big Bang. This universal rebirth could happen over and over again, like a heartbeat that beats through everything. The Big Bounce theory arises from attempts to resolve the paradoxes of the Big Bang using quantum gravity, particularly in a model called loop quantum cosmology. In this framework, space-time is not infinitely divisible, but has a smallest possible unit. When the universe contracts to an extremely dense point, instead of reaching a singularity where physics breaks down, it rebounds. Time doesn't end, it flips. The expansion that follows is a new universe, a new chapter in an eternal book. If this theory is true, then the edge of our universe might be neither far away in space nor long ago in time, but beneath us, in a cosmic layer that came before. Each bounce could bring subtle changes, different constants, forces, or dimensions, meaning that each universe might be similar, but not identical to the last. The idea behind this is that the universe is really just one turn in a much bigger metaverse. Each world rises, spreads out, and then falls back into the deep, just like waves on an endless ocean. The universe takes on a life of its own, breathing and beating to a constant beat. Some people even think that the cosmic microwave background might hold clues to past cycles. Roger Penrose and other scientists have come up with models, like conformal cyclic cosmology, that say weak marks or patterns in the CMB might be the echo of a universe that is dying. When we ask the Big Bounce what lies beyond the edge of the universe, it gives us a beautiful answer. We are there before we are. The universe from the past that has been recycled and will be recycled again. Not a straight line, but a curve that goes on forever. Could life exist beyond our bubble? Could life, intelligence or not, exist in places we will never reach or even see? This is one of the most interesting and depressing questions in science and philosophy. What kind of weird life might be living in the bubbles next to ours, if our universe is just one bubble in a frothy ocean of universes? What crazy ecosystems could form in a world with strange physics, different dimensions, or different time laws? In the world we can see, life is already limited by very specific conditions. This is known as the Goldilocks zone. It's important for planets to have the right chemical elements, be neither too hot nor too cold, and circle a star that is mostly stable. These strict rules make life seem very rare, maybe even magical. But in a bigger multiverse with billions of other worlds, each with its own possible version of physics, the range of possible things could be much wider. In some situations, we might even have to change our ideas about what life means. Could life built on silicon survive in very hot, highly radioactive areas? Could living things be made of pure plasma or patterns of quantum information that are stored in space-time itself? Maybe there are intelligent clouds floating through worlds that look like nebulae, or maybe whole civilizations made up of dark matter beings that we can't see or understand. One interesting angle is the idea that the physics rules we know, which seem to work so well for our life, might not work at all for everyone. There's a chance that fundamental factors like gravity, electromagnetic fields, and the strength of nuclear forces would be different in other worlds. It's possible that some combinations would make worlds too unstable for atoms to form, but other combinations could make things more complicated in different ways. There could still be life, but it might not be built on carbon, need water, or be limited by time in any way we can think of. It's interesting that life beyond the bubble doesn't always mean living things flying around in spaceships. It could refer to systems that copy themselves, change over time, and show awareness in totally different environments. The way we don't know life yet. If we can't see or reach what's beyond, why should we care about it? Because it makes people think and ask new questions. It makes us think about how uncommon or normal our lives may be. Not only does it make the world more mysterious, but it also makes us more mysterious as to what we are in the vast range of possibilities. Do other universes have different physics? What if there was no gravity? It's possible that atoms never formed, or if they did, they would act more like jelly than rigid mass. In a lot of multiverse theories, especially those that are based on string theory and eternal inflation, each world may have its own set of physical rules, constants, and structures. That means that some worlds might be very different from ours, not just in what they contain, but also in how they work. The physical rules in our world seem to be steady and apply to everyone. Light always moves at the same speed. It doesn't matter which way you look at electromagnetic fields. Space and time are warped by gravity, and quantum physics dances around the edges of confidence. But these well-known forces might only be the result of the way things were at the start, or of symmetry breaking that happened when the universe cooled down after the Big Bang. If space is like a cosmic landscape of possible energy states, then each bubble universe may settle into its own unique valley, a minimum energy configuration. That would determine what kinds of particles exist there, how they interact, and whether matter can form at all. Some universes may collapse immediately after birth. Others may stretch and expand like ours, but with different building blocks of reality. In a world with less strong nuclear force, atomic nuclei would not be able to form, and science as we know it would not exist. Or what if protons were lighter than electrons? There would have been no stars, planets, or life. It is amazing how well our world is tuned. In fact, some scientists think that the only way to understand it is by using the multiverse. We live in a world that just so happens to be right for life, because in many other universes, life isn't even a possibility. But these strange worlds might not be empty all the time. If time moves differently, or gravity acts repellently instead of attractively, you could think that order, stability, and even awareness would appear in ways that we have never seen before. Some ideas say that quantum tunneling might let universes hop between physical rules and experience different configurations for a short time, but the physics behind this is only a guess. It's interesting that this idea of different rules also brings up a philosophical question. Is our world the only real one because we can see it? Or are all physically possible arrangements in the same way valid, even if they don't create observers? How would we ever know they exist if some worlds have rules that make it illegal to look at them? The thought that physics is not uniform but unique to each universe is both very scary and weirdly freeing. Is intelligence watching us from beyond? Are we really alone in the universe, or are we part of a bigger picture that is being watched, and maybe even studied by intelligent beings from other universes? This kind of thinking is almost like science fiction, but it makes sense when you think about how big and different multiverse ideas are. One idea, called the cosmic zoo hypothesis, says that Earth and the rest of the world are like an isolated terrarium. They are closed off, contained, and maybe even put there on purpose to keep certain things from getting out. This idea turns the famous Fermi paradox on its head. It's possible that we haven't found alien societies because we're not supposed to. It's not that they don't exist. Now extend that idea from our galaxy or universe to the multiverse. Could there be meta-civilizations, entities so advanced that they exist not within our space-time, but outside or adjacent to it? These beings wouldn't just be aliens in the traditional sense. They might exist across higher dimensions, or operate in universes where time and matter follow different rules entirely. The notion isn't completely unfounded in theoretical physics. If our universe is a brain within a higher dimensional bulk, as in brain cosmology, then other brains, or universes, could be close by. Advanced intelligence might be able to interact across branes, much like a fish might become aware of water currents shaped by a nearby swimmer. We may never see the swimmer, but we feel the ripple. Could these intelligences have engineered our universe? Some theories even propose cosmic natural selection, where universes that are better at creating black holes, and thus potentially spawning more universes, are more fit in a multiversal sense. What if intelligence itself becomes a cosmic reproductive strategy? If such beings exist, they might not only observe our universe, they might have created it. Even though these ideas are interesting, there is no real-world proof to back them. If there are people who are watching, they haven't said a word. No strange gravity waves, no strange energy patterns, and no peek behind the curtain. Then again, would we know where to look? An intelligent being from outside our world could talk to us through topological changes or quantum fluctuations that we can't see or hear. Some experts are interested in the possibility that this kind of intelligence could use our brains or thoughts as a mirror, with awareness itself tuned to pick up faint signs from other worlds. These are wild ideas, but they do point to something important. Maybe just thinking about the multiverse is a way to connect with other people. If there is intelligence outside of our universe, we might never be able to reach it, but it could be reaching us already, in ways we haven't thought of yet. Can signals escape our universe? We don't just see stars when we look up at night, we see signals sent through space and time. Each photon that comes to Earth is a message from the universe. But as we think about what the edge of the universe is like, an even more interesting question comes up. Can any signal get out of our universe? If so, where would it go? Before we can understand this, let's go back to the idea of cause limits. We can only see as far as light has had time to travel since the Big Bang. This means that the world we can observe is limited not by space, but by time. The cosmic horizon is that line, and it's getting wider. But what else? In theory, the world keeps going. What we don't know is if there is a real physical border, or if what's beyond is so disconnected that it can't be reached at all. So, if you aimed a laser pointer into the deepest dark and fired, would it ever leave the universe? The answer depends on what you mean by leave. In standard cosmology, space is not expanding into anything, it's simply stretching. That means the laser light would keep traveling, but the space between it and everything else would also keep expanding. Eventually, the light would be redshifted so much it becomes undetectable, its energy diluted by the growing fabric of space. From our perspective, it would vanish into the void, not by hitting a wall, but by fading into infinity. Of course, what about the multiverse, which is not part of the universe? Could a signal cross over if there are other worlds, maybe as nearby bubbles or branes? There are versions of brain cosmology that say universes may be stacked or floating inside a bigger mass. Although not proven, it's possible that leaks could happen between branes if this is true. Gravity is the weakest force, so it is often thought of as a possible crosser. This could explain why it is so much weaker than the other forces. It could be weaker in other dimensions. Something like gravity might be able to cross dimensions. What about information? Theoretical scientists have thought about wormholes, which are bridges through space-time that could connect not only different parts of our world, but also whole other universes. One way for a word to get to another part of the universe would be to send it through a wormhole. Wormholes, on the other hand, are still just ideas. If they exist, they're probably not steady, especially for something as delicate as electromagnetic data. There's also the idea of quantum coupling, which is the strange action at a distance that Einstein famously didn't believe in. Some people wonder if entanglement could be used to talk to people in other universes. Quantum theory, on the other hand, doesn't allow transmission faster than light, and entanglement can't be used to send information in the usual way. It's a dead end for now. Still, if there were advanced societies that wanted to send a signal to other universes, They might have hidden it in gravity waves or the cosmic background radiation. Or maybe their words are so strange that we wouldn't know what they mean even if they were right in front of us. Are we the edge of another universe? The universe is so big that it's hard to imagine. But what if, in some strange way, we're not the main character? What if we're someone else's cosmic mystery? What if the edge of our visible universe is not only the edge of our own universe, but also the edge of another universe? It's a crazy thought. What if we are the edge of another universe? In multiverse theories, especially those that talk about bubble worlds that formed during cosmic inflation, the idea that there are many universes at the same time is more than just science fiction. It's possible that these worlds are all squished together in a big cloud of cosmic foam. Each bubble is growing and changing, and they may sometimes bump into or affect each other. But in this setting, the word location is hard to define. Someone from another world in this realm might see ours as an edge they can never reach, just like we see ours as an edge we can never cross. From their point of view, we might just be a faint shimmer in the void, a strange gravity event, a faint design in the background. They might have something like the cosmic microwave background, which is full of strange patterns that make us think we might be alive. The same way we wonder if the cold spot in our CMB shows that there is another universe nearby. They might also wonder about their own cold spot, which we made. This is the observer's part turned upside down. We usually think of ourselves as the explorers, searchers, and edge pushers. But this thought makes it sound like we could also be what's beyond someone else's edge. And a line, a fence, a puzzle, a place they'll never get to but always wish they could. In some models of the multiverse, each universe is causally disconnected, meaning no matter how close they may be in a higher dimensional sense, no signal or traveler could ever cross over. The edges between them are permanent and impermeable. But in others, particularly those informed by brain cosmology, there might be subtle interactions. Gravity could seep through, particles could tunnel, and in these moments, the boundary becomes a shared space, however abstract. It's even possible, in models of eternal inflation, that universes are born from collisions, one bubble smashing into another. The marks left by such a collision might be embedded in the geometry of space. If such a thing happened long ago, we might be the product of someone else's universe brushing up against us. And in turn, our own cosmic edge might be the scar from that ancient encounter. As we gaze out at the edge of the observable universe, we're really staring into a question mark, one that challenges not only physics, but philosophy, imagination, and the very meaning of existence. Whether there's another universe beyond, or we're cradled alone in a vast cosmic bubble, one thing is certain: the search will never end. Because in asking what's beyond, we're really asking who we are and how far we're willing to go to find out. If this journey expanded your curiosity, subscribe for more awe-inspiring explorations of science, wonder, and the unknown. And drop a comment below. What do you believe lies outside the universe?